Okay, thank you for that. This program is adapted from something I found on Stack Overflow. It's about 120 lines of code, I think. And it is a really nice parser in terms of being able to evaluate expressions. I'm going to give this to you. I'm going to just talk about it briefly, but let me just show you how it works first. So basically, I can put an expression like 5 plus 6, hit enter, and it gives me an answer. And it uses floating point to do it. I can also do some cool stuff like 5 plus 6 times 2, and it does something like that. I can also get really cool, do square root of 5 squared. Now in C, understand you don't have the caret operator to do power, but in this parser you do. So you can do some sort of expression like that. And
like a mini MATLAB, right?
Yeah, well, yeah, like a mini MATLAB, very mini MATLAB. This doesn't do any kind of graphing or anything. All right, and
so it's what, like an infix to postfix calculator?
I guess it's, I know what the terms infix and postfix mean. It's been a long time since I've done anything like that. So it uses, it's a recursive parser. And again, those of you that haven't had 161, or on, most of you, some of you are taking 161 now, is that right? If you're a computer engineer?
Yes.
Okay, if you're a computer engineer. Okay, some of you probably are. You're going to learn about recursion, where a function can either call itself, or a function A calls function B, which calls function A. And again, I'm only going to spend a couple of minutes going over this. There are many times in your career you will use a lot of code to do other stuff that you didn't write and may not be sure how it works. There are 4 global variables of interest. Global variables are available to any routine, and you'll see that a lot in parsers, even though in general it's probably not a good idea. Expression is a string that contains the expression. CH is the next character being looked at. POS is the position you are within the string, how much you parsed, and len is the length of the string. So in my main program, I basically prompt for an expression, get a string in, as long as it's not equal to end, get the length of it, and then eval is the function which evaluates the expression. And again, it's probably may bother you that I don't have a val of expressions, the expression string in there, but since the expression is global, I don't need to do that. Expression here is the raw expression, that's the evaluated value, and it evaluates it as a double. Once I do that, I print out a question mark again, get the expression again, and keep going till the user types end. Right, there's a function in here called toLower, which just takes the entire string, converts it to lowercase. Again, you can look through this, but eval sets position initially to -1. So when you get the first character, you increment the position and get the 0th character in the string. And then it calls parse and returns that value. Parse calls next character, which puts the next character in the string into CH. It calls the function parse expression. There are 2 pieces of 2 units in this. One is called an expression, one is called a term. actually three pieces, I guess, term, expression, and factor. Note they are expressed in terms of each other. We go down to the bottom. A factor is either a optional plus sign and a factor, or a minus sign and a factor, or open parenthesis, an expression and a closed parenthesis, or just a number, or a function name, or a number, well, factor, which could be a number or an expression, a caret, and another factor. Note the highest precedence here is a unary plus or a unary minus, or a caret to do power. Next highest precedence is either a asterisk for multiply or a slash for divide. Next highest precedence is addition or subtraction. Let me call your attention to one thing here. Parse expression calls parse term. So parse expression calls parse term. Parse term calls parse factor. Parse factor can then call parse expression. Think about that again. This is, again, if you're an electrical engineer, this is the only place you're going to see recursion. If you're a computer engineer, you'll see it a lot more. But parse expression calls parse term. Parse term calls parse factor. Parse factor can call itself, and it can also call parse expression, which starts this whole process again. So you can go deeper and deeper and deeper into functions, and eventually you'll return from this down to the point where this is we just have digits or a decimal point. We keep parsing through it, next character, till we get a non-digit or a non-decimal. And then A to F takes an alpha string, alphanumeric string, converts it to a float, and I give it the address where it starts, which is start position that I marked up here someplace, yeah, up here. So that would return something which would then begin to return back up the stack. Recursion is useful, especially in a case like this. There's certain other problems that are nicely solved by recursion. Okay. In terms of figuring out if something is a function, if you have an alphabetic character, you come along here and these are the functions that it actually, this parser recognizes. You could obviously add other functions if you wanted to without too much trouble. I take whatever the x is, assuming we're in degrees, and multiply it by pi over 180 to convert it to radians. I do not know if the math library on the 328 PB has sine and cosine built in. If it does, I assure you it is a very slow process, but it may have it built in. On the Pentiums and so forth, sine, cosine, tangent, all of your trig functions are actually done in hardware, and so they are incredibly fast. All right, so that is sort of the parser that you're going to be using. Now, we need to go back to, I guess,
so if it's not implemented, do we have to implement it ourselves, like for sine and cosine?
No. Although, well, no, you don't. The I guess the fact is I could have you implement it, but that's more of a C programming project rather than an embedded systems project. For those of you that had me for 160, we probably either did the E problem or you actually found sine or cosine by doing just sort of some sort of an infinite series that each term gets smaller and smaller. And the same is true for figuring sine or cosine. It's an infinite power series where the terms get smaller and smaller.
It was the E problem, and that
It
was
was
the
the E,
one with
okay.
the array of characters.
Yep.
Yeah.
Okay. That's, I don't know, 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial or something like that. And sine is a similar expression that you could figure out. So you could do it, but that's more of a C programming problem. Okay, let's go to, where are we starting? Okay, right here. So this problem that's in the slides is you're going to read a carriage return terminated string. So you type in this, hello, how are you? And as you're typing in hello, how are you, individual characters do not get echoed. So you're just typing to a blank screen. When the carriage return is pressed, you print out the entire string all at once. 8 bits, no parity, 1 stop bit, 9600 baud. And I want to basically have that processor be able to do other stuff. So we're going to use interrupts both for reading the characters in and for writing them out. Right, so always, if it hasn't been drilled into your head yet, where do you start? You start with the data sheet. Again, here are the 5.
So is the lab the calculator, or is the lab this?
The lab is probably a combination of the two, because I've given you code, the parse code we just looked at, that's written for Visual Studio. So it has printfs in it and scanf, or printfs and get string. You're going to need to sort of change those get string and printfs into functions that can be used on the 328 PB. Now, if it probably won't be, it's going to be on Friday, we'll look at how you can write a put character routine for the 328 PB, and then in fact, you can use printf within the 328 PB. So this is leading towards writing a put character, which we'll be doing Friday morning. And so hopefully the parse routine won't have to be changed too much.
All right, and also we didn't have a lab section on Monday, and we didn't get requirements.
You didn't get requirements for which lab?
For this week's lab, unless this is this week's lab and it's been pushed back.
Okay, the lab on Monday should have just been completing the previous lab.
Oh, okay.
Okay,
Then
so,
yes.
So this Friday is the new lab, which is when you'll be doing this. And I don't have a write-up yet, but hopefully today I'll have a write-up for that. Okay, so these 5 registers are what you've got to figure out, what goes into them. Baud rate register is hopefully easy. You just look up 9600 in the table, or I think it comes out to be 103. These registers we've got to take a closer look at. Okay, 103 is what comes, let me make this a little bigger here. Okay, for the baud rate register, I'm going to set it equal to 103. Okay, I said 8 data bits, no parity, 1 stop. So again, you've seen this before in slides, one stop bit, asynchronous 8 data bits, no parity. So basically, all zeros except for our size. The two least significant bits go into control status register C. Most significant goes into status register B. Our interrupt enable bits, we're going to initially set the receive. Where's my cursor there? Going to initially set the receive, enable the receive, and say that the UD interrupt, enable this interrupt. We're not enabling the transmit interrupt initially, because if we enable this transmit interrupt immediately, we would get a interrupt to get a character to transmit, and we don't have anything to transmit yet. So this particular bit is not always going to be set to 1, because it's possible that we don't have anything to transmit. And the initial state is we don't have anything to transmit. The receiver and the transmitter are both going to be enabled. The most significant bit of the character size is 0, because we're doing 8 bits. We're not doing 9th data bit at all, so those can be zeros. All right, so let's go to the next slide and look at this. When a character is received, so when we start this program running, at some point, we're going to get a character in. When that character is received, I am going to want to generate an interrupt. This particular bit is going to be set. So when I write something to the UDR register, the data register on the UR, it will generate an interrupt. That has more to do with the transmitting piece of it. But I can set that as long as this transmit is 0. And that's how I'm going to control whether I'm transmitting anything or not. Okay, for my main program now, to control which character of this array S I'm transmitting, I've got a index for inputting and an index for outputting. That is, when I'm receiving characters, they're going to go into this S array, and that's going to be controlled by index in. When it comes time to output, I'm going to be using index out. I initially, I'll admit, I just had one index variable, but if you are outputting something and at the same time it's being output, you begin to type, that creates a problem. At 9600 baud, it probably would never be seen. I think I tested this doing something at 300 baud, where if you're printing out, say, 100 characters at 300 baud, it's going to take you, 30 character, it'll take you about 3 seconds. So you can conceivably type ahead of the output, and then you have a problem with characters appearing at the end when they shouldn't. So separate index into S for inputs and for outputs. Something that I haven't done so far, but I did here, is I created a separate routine to initialize the UR. So you know where all the initialization stuff is. I enable interrupts and then spin. So most of the time, unless we're typing characters or printing characters, this while loop is going to spin, and I could do all sorts of other stuff in there. All right, let's look at the setting up the registers here. Right, we've done this a few times before. Not multiprocessor mode, not ×2 baud rate. Here I've enabled the receive interrupt. I've enabled the UDR interrupt. I've enabled the receiver and the transmitter. In this case, I've done Asynchronous mode, no parity, 1 stop bit, 8 data bits, and we're not doing a regular polarity. Okay, in the code, despite the fact I said 9600 earlier, that is for 300 baud. I should change that to 103, but let's leave it at 300 baud for the moment. Okay. Now, okay. Here is where cool stuff happens. Remember, in the main program, all I'm doing is spinning until such time as the user types a character. When the user types a character, because the receive interrupt enable was a 1, the receive interrupt enable flag is a 1. When the user types a character, I'm going to come to this interrupt service routine. I grab the character that was received out of the data register, and I check to see, is it a return or an enter? If it's not a return, I simply add that to the S array, the character array, at location index in, and I add one to index in afterwards. So the very first time I've got a character that's received, if it's not a return, I put it in S sub 0. I add 1 to index in, it becomes 1, and I'm done. I go back to spinning in the while loop. Next time I come in, grab the character in the data register. If it's not a return, I'll put it into S sub 1, add 1 to index in, increment index in, it becomes 2, and I'm all done. And I'll repeat that multiple times. When the character typed in is a return, I go to the else part here. I terminate that character with a null, just to be polite, and I reset index in to 0. That is so if when I get out of this routine, if I immediately get another interrupt, which if I immediately get another interrupt, that would actually cause a kind of a problem. But given how fast this runs, it shouldn't be a problem. I add a carriage return line feed onto this, and then look at this line. This is kind of a really cool magic line. I set the okay, UDR interrupt enable. Let's go back and look at what this particular bit does on the data sheet. Data register interrupt enable. So this is on data register empty. Let's go back to here. Okay. All right, this isn't the interrupt enable bit. This is the data register empty bit, but we'll go back into interrupt enable in a minute. This indicates if this bit is a 1, and note initially on reset it is, and we haven't done anything to change it. If this bit is a 1, it means the transmit buffer is ready to receive another character. So we haven't transmitted anything. We don't have anything in the transmit buffer. So this bit is always going to be 1, saying the data register for transmit is empty. If we go back to this interrupt enable bit, that is going to generate an interrupt if the data register for transmit is empty. So the fact that I just set this bit to 1 means I can now it will generate an interrupt. Let's go back to the code. So as soon as this bit is set to 1, what's going to happen? As soon as the moment I return from this interrupt service routine into the spinning while loop, a data register empty interrupt is going to get generated, and I'll end up in this routine. All right, so I'm going to check and see, is character 0 a null? It won't be, because there'll at least be a carriage return line feed in there. And if it's not a null, I'm going to set the data register equal to the 0th character in S. So if I typed in Star Trek, it would be set to an S. That is immediately going to begin to get transmitted. And I return. What happens now? No interrupts are going to get generated until the S in, I take that back. Okay, I've sent the S in Star Trek to the data register. The data register is immediately transferred to the transmit shift register. Remember that diagram that had the data register, which got loaded into the transmit shift register. So I loaded something into the data register. It would immediately get loaded into the transmit shift register by the hardware, because there was nothing else in there. And it begins to transmit that character out 1 bit at a time. The data register can now have something else put into it. So as soon as I return from this interrupt service routine, that DRE flag is going to get set to 1 again. This interrupt service routine is going to get called immediately again. And I'll put the first character of the array S as a T, as in Star Trek. I'll put that T into the data register. Now the hardware is going to be kind of smart. It knows that there's still something in the transmit register. It's not going to move that, or it's not going to load that character in the data register into the transmit register until the transmit register is empty. So I return from this routine, and it will be several hundred microseconds, depending on what baud rate I'm doing, before the character in the data register gets put into the transmit register. In that time, we're going to be spinning in the while loop and doing nothing else. As the current contents of the transmit buffer, the S in Star Trek, is shifted out 1 character at a time, 1 bit at a time. When that first character has been shifted out completely, the hardware will automatically take what's in the data register, again, move it to the shift register, and then raise that flag again, generating an interrupt. Data register empty. We'll come to this interrupt service routine again, grab the A in Star Trek, put it into the data register, and continue on. That's going to take, quote, a long time, probably several milliseconds, depending on the length of the string and the baud rate. When the next character to be transmitted is a null, that says it's the end of the string. Up here, just to alleviate any ambiguity, I ended the string with a null. I then concatenated a carriage return line feed onto it. String cat is going to look for a null at the end of the string, remove that null, replace it with whatever's here, and then put a null at the end of it. So this null right here is going to be short-lived. It will be replaced by a return, new line on the next byte, and then string cat will put a null here as well. So I will have output a carriage return line feed, then I see a null, and then I AND it with not this. So I set that bit to 0, and it's not going to generate any more data register empty interrupts, and hence, and then I also set the location in the S buffer to be 0. All right, that's the code. Again, not a whole lot of lines of code, and we've sort of built a echoing terminal kind of a thing. All right, so this would be the output, but we're going to look at the events. I initially here would type space the final frontier, and the screen was still blank. So I typed all of that, screen was blank. When I press enter right here, so I've typed a whole bunch of characters, cursor's just flashing at me. When I press enter, I see space the final frontier. Carriage return new line, and the cursor is blinking here. You type these are the voyages of the Starship Enterprise. And nothing, even though I've typed, I don't know, 30, 40 characters, nothing is echoed until I press enter. Same thing here. Now, suppose I wanted to echo each time, what could I do? I have to modify the software a little bit to make it do that, and I could certainly do that. Okay, questions on that? All right. All right. The rest of slides in this package, we're doing in time. Okay, good. Rest of slides in this package are just out of the book. You can look at them. They may or may not, probably they're not 100% compatible with the 328 PB, but they've got a lot of good stuff in them. Let us now look. Right. Two routines. I will tell you in the evolution of this course, going back 15 years, at one point in time, a great guy by the name of Dave Lincoln taught this course. Then I taught the course, then Ben taught the course, and now I'm teaching the course again. I'm going to give you access to two different routines. You are welcome to use whichever ones you want. One was written by Ben, one was written by me. We have pedagogical differences as to whose is best. I'll let you be the judge of it. I should probably tell you, in a production environment, Ben's is better than mine. I wrote mine with the understanding, or with the thought that you would be able to understand it, even though it contains a lot of address, call by address stuff with the asterisk. My thought is, if you did really well in 160, you should be able to understand it. In Ben's method, which I'll look at in a minute, unless you have had 161, you probably are not going to understand it. So that's the difference in the writing.
But it's probably a tad more efficient because it uses passing by reference, right?
Now, I would say Ben's is probably more efficient. And again, in a production environment, Ben's would be the one that I use. I kind of use this, especially when I taught 161, we kind of did stuff like this. We created a queue routines, NQ, DQ, things like that. So I think you guys are in the sequence. You've already had 264, right? You had 264 last spring, most of you, okay. Did you do some stuff with NQ queuing and DQing? Did you look?
Not explicitly.
Not explicitly, all right. All right, for what it's worth, next fall I'm going to be teaching 264 again, so I will go back to doing NQ and DQ.
We're doing that right now in 161, NQ and DQ.
Oh, okay, so basically NQing and DQing is putting something in a line. The thing that you can probably all relate to is when you send something to a printer at the university. It goes into a queue. If 6 of you submit a print job at the same time, you don't want page 1 of person 1's to print, then page 1 of person's 2, page 1 of person's 3. You want the entire job to be whoever happens to get there first. The first job prints, and the remaining jobs are in a line or a queue. When the first one finishes printing, the second job prints. Queues have a server or a dequeuer that processes the things in the queue, and they have a supplier or an NQer which puts things into the queue. So what I have done, if we just go down here, here's a couple of interrupt service routines. One when the receive register has a character in it. The other is when the data register is empty. Let's see, let's look at the, when I receive a character.
Oh, so you're just using a queue instead of an array.
Yep, exactly.
Oh, okay. And what's with that weird dot delimiter? Is that just visible formatting on the document?
Oh, yeah, I like to, in Word, I like to see the tabs and the new lines and everything. So that look better? Okay.
Yeah, better.
Yeah, I'm so used to it, it doesn't bother me, but okay, I can see where it would be confusing. So queues have a head and a tail pointer. That is where you're getting something from if you're dequeuing it, where you're putting something if you're NQing it. A queue as implemented here is really the array buff, and it's almost drawn as a circle. So as you start to put stuff into the queue, you can go 0, 1, 2, 3, 4, 5, 6, 7, 8. I think I go up to 250 or 255. The next location to put something after location, say 250, is location 0. Now, hopefully, as you're adding stuff to the queue, there is also a server dequeuing stuff. So before it comes time to go from location 250 to location 0, the dequeuer has taken some stuff at location 0 and 1 and 2 and 3 and made use of it, whether it's a print job or transmitting the character or whatever.
How would you know when it is time to dequeue something?
Okay, how do you know when it's time to dequeue something? Whenever the whenever the data register is empty, it would be time to dequeue something. So anything that's in the queue, you're going to want to transmit. Right. So if we just look, I think the data register empty is a little bit easier. That's for transmitting. Okay, well, yeah, okay, that's for transmitting something. So if I'm going to, if it's time to transmit something, the data register is empty. This interrupt would automatically get generated, and I check is empty. If there's a certain condition of head and tail that denotes the queue is empty or the queue is full, and they're similar but not exact. So I'm looking at this is empty, compare head and tail. If it's not empty, meaning there's something to transmit, I dequeue, get the next thing out of the queue into CH, and I send it to the data register. At which point, as soon as the transmit shift register is finished, the data register will get loaded into the transmit shift register. If the queue is empty, I'm going to set that interrupt enable for data register empty to 0, meaning interrupts are no longer going to occur. when I receive a character, this interrupt gets generated. I immediately put that into the queue. I get it out of the data register. Keep in mind, I said this last time, I haven't emphasized it today. Data register when I'm reading from it, data register when I'm writing to it are two separate locations. I really think it's poor planning on the part of Atmel to name these the same thing. But this location when I write to it, this location when I read to it, even though it's the same name, it is a separate set of bits, separate set of 8 bits. So if that's confusing you, I hope that cleared it up a little bit. I've got a receive interrupt. That means there is a character that has been received and put into the data register for the receiving side of it. I'm going to grab that. I'm going to enqueue it, put it in the queue at the end. If it is a return, I'm going to also force another character after it, a new line. So just because whenever you receive a carriage return, generally you need to do a carriage return line feed. In the event of a backspace, which is the escape character \B, I basically put a null where the character should have gone, and I back up the index by 1. All right, so if it's not a return and it's not a backspace, I put it into my token array. I always make sure that the token array is null terminated. Okay. All right. Now, let's go back to main for a minute here. All right. Let's look at the all right. Let's look at my output a string routine. Anytime I want to output a string, basically I need to stick it character by character into the queue. And each time I pass head and tail, as well as the character I'm enqueuing. Buff is going to be my my queue, the routine that gets characters added to it. Okay. To initialize my queue, I set head and tail equal to 0. There's an overflow flag here, which probably isn't used enough, but gets set initially to 0, meaning no error. I mentioned a few minutes ago about queue being full, queue being empty. If head and tail are equal, be it 0 or anything else, when head and tail are equal, the buffer is defined to be empty. As soon as I put something into the queue, tail would get incremented to 1, meaning that's where I put the next thing. Head is where I get the next thing from. When I look at an is empty condition down here, I compare head and tail with each other. And if they are equal, this would return true if it's empty and 0 otherwise. Just some other functions that you would normally do with a queue. PQ can frequently look and see what's in the queue without actually removing it. You might want to see if there's a null next in the queue. You might want to see if there's a carriage return. I don't think I use it in any of the code, but it's here. If it's empty, I'm going to return a -1. Otherwise, I just return whatever's in the buffer and don't update header tail. Okay. All right, so look at this. Let's look at the NQ and DQ routine, and then I think it's about time to, we're almost at the end here. When it comes time to DQ something, that is take something out of the queue, I check to see if if the queue is empty. If it is, I return -1. Otherwise, I return whatever's at the head of the queue. And then I add 1 to the head pointer, mod size. Okay, size is a number of elements in the queue where I wrap around from 0, 1, 2, 3, 4, 5, 6, 7, 8, and so forth, up to say 250. The next location after 250 is location 0. So if I have, say, 250 elements, or 0 to 250, for my elements, that's actually 251 elements. So when I go from location 250 now, plus 1 is 251, mod 251 gets me back to 0. And I would return the character. Since I am taking something out of the queue, buffer overflow, even if it's occurred previously, now is no longer a problem. To NQ something, here I check to see if the queue is full. So if tail plus 1 mod size in the case of wrapping around at 0 is equal to head, that's an overflow condition, and I just set that flag to 1. Otherwise, I take whatever the new character is to be NQ'd, put it into the buffer at the tail, and increment tail, wrapping it around just like I did head. All right. For a pre-lab, which is not so much going to be graded, but I strongly suggest you should do, type in some of the programs we've looked at and make sure you can send a character to the 328 PB, maybe echo it back, write some of these string characters, string routines, and ultimately there's nothing to prevent you from starting on the lab now. On Friday, I will do, how to create a put character routine and a get character routine, which is sort of a modification of these routines. And then turn you loose with the lab. Okay, barring any crisis, I will have office hours at 3 o'clock today. If anybody wants to talk to me, the way that that can work, if anybody wants to talk to me individually, we can go to a breakout room. Otherwise, we can gather as however you want. So at 3 o'clock today, I will be on, and I'll send you a link, which will be good for all office hours. Any questions?
When is the lab due?
Again, about a week from Monday, but I'm lenient. That's we have been encouraged at every level of the administration to be lenient given these times. So, but my hope would be about a week from Monday you'd have it done. A week from this coming Monday you'd have it done. Any other questions? Okay, I will either see you on Friday or this afternoon. Blessings to everyone.
You too, Professor. See you.
Bye. Thank you.